Hey guys, welcome to another video. So what we're going to talk about in this lecture is rotational dynamics. So we're going to talk about rotation and how it differs from linear translational motion, which is the motion that we've really been talking about this whole semester. So first of all, I guess what we need to do is differentiate between translational motion and rotational motion. So translational motion is when all the pieces or particles that make up an object move at the same rate together. Okay. So, for example, you've got some box, okay, and you've got tons of particles within that box, right? Tons of pieces. And if the box moves to the right, all of those pieces move at the same rate, okay? Because the pieces of the box, they're all roughly static, okay? At least on the macro level. And they're all going to move together if this box moves to the right. If the box moves down, they'll all move down. If it moves to the left, they'll all move left. If they move diagonally, they'll all move that same amount still, okay? And the reason this is true for us is because we've treated, we've treated objects as point particles this whole time, which means that like a box becomes, so a box just turns into a particle. So because everything's a particle, everything's moving at the same rate. Right? This one particle, it's the only particle that exists within that object, so it has to move at the same rate as itself, right? Everything, which just is that one particle, moves at the same rate, okay? So you must be wondering then, if things aren't moving at the same rate, what happens? Well, so to not move at the same rate, we need solid objects, okay? So it's stuff that we haven't talked about. So the box now is a box, okay? But more than that, we need something known as an axis of rotation, okay? So we need something to rotate about. Actually, that was spelled right. And let's move this. Okay. So now what we can do is if we rotate this box, about the axis of rotation, we rotate it this way, so it's going to move this way. These pieces of object now that's in this thing, this closer stuff only needs to move around this track, right? To move in a circle. But if you're moving the whole thing, right, everything's attached to it. And so these guys, to move in the whole circle, has to move this amount. So rotational motion is when objects do not move at the same rate. Is when pieces of an object, or different objects if you're talking about a system, okay? And so, and it's simply because, these outer pieces have to go farther than the inner pieces, right? And so as you can imagine, we need to, to account for this, we need new physics, okay? That's based on the old physics. So it's new physics, but based on already know. Okay. This lets us discuss rotational motion and solid objects. Okay, so no longer just treating things as point particles. So to start this, we need to basically, so to start this, we need to redefine some terms, and we will go through all of so we will go through all of the physics we've already covered, okay, and apply it to these new ideas, okay? So to start this, we're going to redefine some terms, and then we're going to go through all of physics that we've kind of already covered and apply it to these new ideas. So we will discuss kinematics, forces, energy, and momentum as we go through and discuss rotation as a whole. Okay? So, let's start with our discussion of kinematics. Okay? If you remember, we started kinematics by discussing position, velocity, and acceleration. So we started this by discussing position, velocity, and acceleration. And so we're going to do the same thing there, but we're going to do it for rotational position, rotational velocity, and rotational acceleration. So for rotation. To do this, here's a diagram. So here's a diagram to get started. You're going to need the axis of rotation, okay? So this is our axis of rotation. Pretend that this is a good circle. I almost kind of want to redo the circle because it's that bad. Okay, that's better. And if I move the axis of rotation, that's a little bit better. Okay, and then what we need to do is we need to draw a couple other things. Use green here. So I'm going to define this angle theta, theta initial, theta final, and I'm going to write the script L. Okay, the last thing we're going to do is write R here. Okay, so now let's define some terms. When you're discussing rotation, you're going to have the same thing that you have with kinematic rotation, right? You have your initial position, final position. So theta initial is your initial position, okay? Just like x initial for linear rotation. Theta final is your final position, okay? Because if you want to discuss position, you need an initial and a final, right? You need to know how your position changed, usually per time for velocity and things like that. L is the arc length, okay? This is your position traveled, okay? Theta is the angle made relative to axis of rotation. R is the radius of the circle made by rotation. Okay. Now, how do you discuss position? Well, in linear terms, how you discuss it is you talk about it in terms of, you can talk about it in terms of feet, inches, right? You're like, oh, I went 12 feet, or I went like 30 feet, or I went like 100 inches, right? Or maybe like you're talking about long distance, you're talking about things in terms of light years. But we use the SI unit of meters, right? So for linear motion, we use meters, okay? Because it's the SI unit. So the SI unit for rotation is the radian, okay? So it's not actually degrees. It's this term called radian. So let's define it. So radian right here defined. And this is defined as the angle subtended, okay? So that would be, well, I'll just write the whole thing and I'll describe it. So the angle subtended by an arc whose length is equal to its radius. Okay, so let's look at this. Defined as the angle subtended by an arc, right here. So here's the angle that's subtended by this arc, okay, whose length right here is equal to this radius. That is 1 radian, okay? If you use geometry, so and fancy derivation, it's not that fancy, but I'm not going to do it in this lecture. I believe your book has it. You can derive this formula. Okay. The angle equals the arc length over the radius. Okay. And if the arc length and the radius equal each other, that's the definition of a radian. That's 1 radian. Then your angle would be equal to 1. Okay. Here, the more popular form, I believe, okay, is L equals R theta, right? You just multiply that guy over. And using L equals R theta, we get this relationship between degrees and radians. Okay. So if your arc length is the entire circle, right, 360 degrees, okay, and that can equal 2 pi radians, okay? And so you must be thinking here, well, I'll describe it in 1 second. I'm going to just divide this over, okay, going to move this over real quick. (360) over 2 is 180 over pi equals 1 rad. Or you could multiply this over and get 180 degrees equals pi radian. Now, I've actually taught you that your units on one side of the equation equals your units on the other side of the equation. So in this case, wouldn't a degree be a radian? Yes. Both are technically dimensionless, and so you can kind of see it here where the length is over the radius, which would both be in units of whatever. Maybe the arc length, you know, is in meters and the radius is in meters, so meter over meter means that angles are dimensionless. That's technically true. But we assign, you know, these terms, radians and degrees, to discuss the system we're talking about. Okay, so these are just these are assigned, okay, but they're technically mathematically dimensionless. And so if you look in your textbook, especially with derivations and stuff, you'll see them kind of switch back and forth between radians and just using the number 1. Don't worry about it too much. All you really need to know is this conversion. Okay. So this conversion, if you're looking at it, so you get 90 degrees. This is just a typical coordinate system. Okay, in degrees, right? And you're rotating that way, as is convention. You rotate counterclockwise. 0 degrees and also 360. Okay, this is 0 radians and 2 pi radians. Okay. This right here is pi over 2 radians. this right here is pi radians, and this is 3 pi over 2 radians. And if you want a number assigned to it, you can plug it in right here, pi, but 1 rad is roughly, like if you just divide 180 by pi over here, you're going to get 57.3 degrees, if that makes you happy to have a number assigned to it. Okay. Another popular one to define is 45 degrees, and that would be pi over 4 radians. Okay. These are the ones that you probably want to at least think about, not necessarily memorizing, but getting familiar with, as it will make your math a lot easier. Because again, radians are the SI unit. Use radians for a lot of stuff in rotation. It's good to get familiar with it. This is also why when we were doing problems the whole time, before this, oh, your calculator was in radians and not in degrees. It was using this method of measuring, okay? We're discussing rotation. Additionally, one last conversion you may see a lot is that 360 degrees is 1 revolution, or 1 rev, okay? This is used in a few problems. It's just to throw you off your game a little bit. I'll try to go over that when we do those example problems. So, just to sum up, rotational position is measured in radians, okay? 1 radian is 57.3 degrees, if that makes you happy. And is similar to translational position, the definition, where you have, so you've got translational here, and this is delta x equals x final minus x initial. Rotational. This can also be called angular. You'll probably see me also called. You'll see me interchangeably use angular and rotational when it comes to this stuff, but use the symbol theta, and it's theta final minus theta initial. You may also see I as opposed to O. I kind of interchangeably use those again. O's a little bit easier to write. These units are radians. Okay, so that's position covered. Okay, so we've covered position. Let's do velocity next. So velocity next. So angular, I've been calling everything rotational. Let's do that. So rotational velocity, again, also called angular velocity. So it's going to be the change in position over change in time. And we use the symbol omega, tiny omega, okay? And the units are radians per second. And just for comparison, the linear case or translational case is delta x over delta t equals v, okay? Right? So there's your comparison to that. Okay, so this is the rate. So that's the comparison. This is the rate. So angular velocity is the rate at which you move about an axis of rotation. Okay, just like the translational case, where it's the rate of motion, right? And instead of comparing to a coordinate system, that's a, just like that, like a typical Cartesian system where we measure everything from a point of origin, we have an axis of rotation instead. Okay, so still an origin in a sense, we're just moving in a circle. As usual, there's also instantaneous and average. Angular velocity. Like you can basically rotate, you can pick up speed and slow down as you're moving around that circle. But we don't need to make those distinctions because we won't be solving those problems. But you can certainly do it. Just know that it exists. Okay. Next up, we have acceleration. And you can probably guess what this will look like because it's basically the same thing. We have our delta omega now over delta t. And this will be alpha. That's what this is known as. So this is called alpha. You may have seen this. Sometimes it's used if you're out of theta and you're out of gamma for angles. You may use alpha. But here, it's used for rotational acceleration. The units are radians per second squared. Okay. And the translational analog for this would be the delta, velocity over delta time equals a. Okay, so very, very similar definitions here. Okay. There's one other thing I need to discuss before we kind of break this wide open. There's like two more things. And then I can give you the rotational kinematic equations, which will look familiar. Okay. But there's relationships or equations for linear and angular quantities. Okay. So x, which is linear, equals the radius times theta, okay, which is our angular. We have v equals the radius times omega, and we have a, the tangent acceleration. I'll talk about these two different accelerations. Equals r alpha. So now expanding on this a bit, let's just expanding on this. If you're moving about an axis of rotation, something, your net acceleration will be in this direction. Okay, so this is your a for your linear acceleration. It's tangent to the circle, but it's also composed of two different other accelerations. Because it's a vector, right? You can break it into components. And those components are a, the tangent to this, okay? or this is the tangent acceleration. Sorry, it's probably a poor choice to say this was tangent to the circle and this being the tangent. Don't worry about it. This is the one that, this points along the circle, I guess. Probably poor choice of words. Anyway, actually, let me redraw this just a little bit. Make it a little bit easier to understand. Okay. In. I think we'll do one problem. There might be a little bit more than that with this sort of thing. So, we have multiple accelerations when, there we go. Actually, let me draw these as blue. This look better. Okay, so this is your net. This is your net acceleration. Okay, this is the result of these two guys. This is your tangent acceleration, and this is a function of your rotational acceleration, and multiplied by your radius. Okay, so if you have a smaller radius, that will change your tangent acceleration. Okay, if you have a bigger one, right? This guy is actually just called your AR, or your AC. This is your centripetal acceleration, okay? And it points inward. So what happens with rotation is that essentially AC is the acceleration that's caused by what is the acceleration that's caused by the thing that's causing the rotation in the first place. So you've got some object that's moving, okay? It's moving to the right or something. But then maybe it's like a ball and you've got a rope on it and you're pulling inward on it. That causes an acceleration inward. That's what this is. And so you've got this object that's moving and you're constantly pulling it in. When you're constantly pulling it in towards the center and it's moving to the right or moving tangent, that's what causes rotation. And that is what causes these three accelerations to exist, okay? So there's three accelerations, and this is just the equation for one of them, okay? You can also do what you can do with other vectors, where you have A can equal A tan plus AC. And you can also have one other equation here, like this, okay? Or I'm going to write it just to keep it with its same structure, okay? So once again, A is net accel, AC due to the inward force causing rotation. Okay. All right. A couple other definitions, and then we can get to the important equations to discuss kinematics when it comes to rotation. So a couple other definitions here that you may see. That come up when you're talking about rotation. There's frequency, which is number of complete revolutions or rotations per second. So you get F equals omega over 2 pi. Or you may see this as omega equals 2 pi f, just multiplying that over. And if you're curious, this is the distance, this is the rate, okay? And so that should make sense to you as to why that equation is like that. You get velocity over distance. That should give you the frequency. The unit is the hertz, or 1 rev per second, or it's written as inverse second, or 1 over second. I usually see the hertz as 1 over second most of the time. Okay. You can abbreviate this as Hz. Okay. There's one other thing, and that's the period. Okay. So the period is the time it takes to complete one revolution. Okay. And T is the symbol for period. And it's because units are seconds. So it's basically like time, which is why they use T for it. So it's 1 over the frequency. Okay? And units are just seconds. Okay. So with all of that, here are the rotational kinematic equations and their linear analogs. Okay. And these look very, very familiar to, or should look familiar to you. They definitely will after I write out the linear ones. For completeness, I'll write the average, using a bar for average instead of the vector. Okay, so V final equals V initial plus AT. Omega final equals omega initial plus alpha t, right? We have X final equals X initial plus V naught t plus 1/2 AT squared. Here we get omega final equals omega initial plus omega initial t plus 1/2 alpha t squared. Okay, same thing. And if this surprises you that these equations are basically the same thing. You just swap out the angular term for the linear one. Um, the reason they're the same thing is they were derived under the same laws of physics, right? F equals ma. And so it's not like just because you're rotating, it's not like the laws of physics suddenly change. And so, of course, these guys look the same. They should. Okay. So that's rotational kinematics. And those types of equations will, or those types of examples will work the same way, where you will have, like, your knowns and unknowns and all of that stuff. So, one reason I like doing rotation at the end of the semester is that it gives you a good recap of what you've learned. Okay. So, we've done kinematics. Let's look at rotational forces. Okay. So let's look at a wooden beam that's rotating. There's a few things with forces we'll discuss here, including how we get rotation in the first place. So because we're now dealing with solid objects, okay, we've now got a solid beam. We don't just have a particle, right? This beam is one continuous thing of mass. It's very different. Because we have a continuous piece of mass, how we apply forces matter. So if I push up here, that's very different than pushing in on the wood, right? On the wooden beam. So if I were to push on something into the axis, like your door, like imagine a door, you're pushing into it, it won't rotate, okay? But I mean, you can take, so if I treat my finger as the axis of rotation, right, and I push in on my phone, it's not going to rotate. I have to push up on some level to rotate about my finger. And so the same thing is true here, in that how you apply the force matters. Okay? And so here's the equation for that. So torque is going to be the byproduct of this. Okay. So the axis or here, let me write it like this. So the relationship between the distance from the axis and the distance from the axis of rotation and how you apply the force relative to the axis of rotation. Results in what is known as torque Okay, so let's look at this. Here's the equation. This is what's known as a cross product. We've dealt with a dot product before, but this is a cross product, and here's torque. It uses tau, okay, and this is torque. So that symbol is tau, which is the symbol for torque. Everything is a vector, and there's a cross product in between, and this is the radius or distance to axis, which is like the radius, how far out you are, kind of. And this is the force applied. So let's look at this real quick. F maybe I want to use different colors, I don't know. R. This is our angle between them, theta. Okay. And the torque that results is actually perpendicular to both of these. So with a cross product, well, let me discuss what a cross product is first. So a cross product is used when you want to know about the difference between two vectors. Remember, a dot product was when we wanted to know how similar they are, right? If we had, we were pushing on a box or something and we were pushing to the right and the box was moving to the right, those vectors weren't different at all, and so the work applied was maximum. But if we have them be 90 degrees apart and the force you were applying was perpendicular to the work, then no work, or perpendicular to the displacement, then no work was done at all. The opposite is true here. We want these vectors to be as different as possible, right? So if you're pushing on something, and I'm pushing into the axis of rotation, so my phone, right? I'm pushing into it. How much does my phone actually rotate when I do this? None. Because they're not perpendicular to each other. But if I'm with my axis of rotation and I push up on my phone, it's really easy to rotate it, okay, because they're perpendicular to each other. So the more different they are, the more rotation happens and the more torque results. So like the dot product, we can reduce the equation. So we don't actually need to solve for the cross product. We can get around that. Or, since we're talking about magnitude now, I'm just going to take that off. And sine theta, again, is used because sine of 0 gives you 0 if there's no difference between r and f. And then if there is a big difference, 90 degrees, this becomes 1, this becomes maximum. Okay, so because it works for discussing I cannot read that at all. the difference in R and F's direction. 90 degrees. The max value for or I guess just, yeah, for sine theta. Because if you don't know, sine varies between 1 and -1, just like cosine theta does. So now let's discuss torque's direction. So, or I should say, the above equation gives us the magnitude of the torque. The resulting direction because remember, torque's a vector, and this only gives us the magnitude, right? But the resulting direction of the torque can be determined either by the cross product or via the right, I guess I should write it out because it's the first time you're seeing it. The right hand rule, okay? And this is abbreviated as RHR. We will do more stuff with right hand rule in physics 2. And if we're doing it in this, for an example, I'll show you how to do it. But just, so I'll show you in examples if we need to. If needed. Just know that torques will be perpendicular to both R in the above example. This is either into the page or out of the page. So if you look at this perpendicular to both, you have the radius to the left, you have force up, so that means we need to go into the z-axis or the other dimension, which is either into the page or out of the page, okay? And I can, like I said, if I need to, I'll show you how to do that and determine which one that would be, okay? But torque will increase or decrease as the ease of rotation changes. So if it's easy to rotate, you'll have massive torque. If it's harder to rotate something about an axis, you'll have a smaller torque. Okay. Oh, one last thing I forgot to mention. Because torque is a function of the radius and force, The units are Newton meter. And Newton meter, you remember, are joules. So this will give something rotational energy, okay? Okay, so next up, we're still talking about forces, so we have an analog for Newton's second law. So remember that when we were discussing forces, the big picture there, the big thing that we talked about was Newton's second law. And if you remember, that was a really poor sigma. F equals ma. This turns into the sum of the torques equals I alpha. And this is our quote-unquote mass. Okay, this is our moment of inertia. Okay, this is moment of inertia. This is our rotational acceleration. So if you remember in our linear discussion of forces, you summed up all the forces, right? And how you accelerated depended on how much mass you have. Mass is your resistance to forces, right? If you're more massive, it's harder to move something. Here, the same thing is true. You sum up all the torques, that's equal to your mass, and if your moment of inertia is larger, or distributed in a different way, I'll talk about that, that will alter your rotational acceleration. So, let's discuss moment of inertia. I is known as moment of inertia, and it's an object's resistance to rotational motion. It's not just a number like in linear motion, okay? Because objects now have continuous mass, they now have form, they now have shape. That changes. So depending on shape and how mass is distributed, throughout an object. For the wooden plank, for example, I is 1/3, this is mass. We use big M for continuous objects. This is the length, okay? So the longer it is, the more moment of inertia it has, the more resistance it would be to motion, okay? So there are many different I's. And you'll either solve for them or I'll give them normally, okay? You usually don't need to memorize, so don't. All right. Next up, rotational energy. and momentum. So let's start with the energy first. So for work, we always had work, right? And that was, you know, force, distance, cosine theta, right? The analog, okay, not right. The analog to this is work, tau, and then change in your, so this is your force times change in distance, right? This is your tau times change in angular position. Okay, so it's basically the same thing. Also, once an object is rotating, it has rotational kinetic energy. And so the Ke for rotation is 1/2 I. This is for the center of mass of it, because you're going to be rotating about its center of mass, serves as its axis, omega squared. And then again, the linear thing here was 1/2 mv squared. So m is replaced by I. Okay. An object rolling down a hill has so how this will work, for example, an object rolling down a hill, you know, something like this. Not only is it moving linearly, but it's also rotating. So the Ke total is going to be 1/2 I omega squared plus 1/2 mv squared. And it also has gravitational potential energy. Okay, so that's how problems like that work. You have to take account of all the energies at once. So remember to take all energies into account. Okay. Conservation of energy. Still a thing with rotation as well. Okay. You can still conserve energy with it. Keep that in mind. For momentum, remember linear, we have P equals mv, and then for angular, we have L equals I omega. This is our angular momentum. I again taking the place of m, omega taking the place of v. And remember how we rewrote Newton's second law? You can do that again in terms of momentum. So tau now equals delta L over delta t, whereas the linear case delta P over delta T, okay? There's still conservation of angular momentum as well. We'll do a couple problems with that. The biggest example, the one you'll always see is that, you know, figure skaters pull in their arms that looks awful. Pull in their arms while turning, and then spin faster as a result. The reason that happens is when you're doing this, your arms are spread out, your moment of inertia is larger, and so as you pull in, you're reducing your moment of inertia or your resistance to rotation. And so that increases your angular velocity as a result. So this is because your I decreases and omega increases. So your decreased mass, increased velocity. This is just what we did with conservation of momentum, right? If you're increasing your mass, you're increasing your mass, decreasing your velocity, or decreasing your mass, increasing your velocity. So this is the same as linear momentum conservation, where mass decreases, V increases, okay? Or vice versa. All right. There's one more thing. Let's just do a summary now. Just to make sure I've covered everything and you guys get everything in one place. Summary of rotation. I know there's a lot here, okay? So I want to make sure if you remember nothing else from this lecture, remember that it's basically the same thing as linear. You're just swapping up the terms. Okay, remember radians and all of that. So we have position. And then we had delta x equals x final minus x initial over here. The units are rad, revolutions, or degrees. Over here is pretty much just in meters. We have velocity, delta v. This is, sorry. rad per second, revolution per second, degrees per second. Over here, we had, in the linear case, we had V equals delta x over delta t. This is in meters per second. We have acceleration, alpha equals delta omega over delta t. This is radians per second squared, revolutions per second squared, degree per second squared. And then, of course, the linear analog for that was the change in velocity over change in time. The other accelerations are due to what causes rotation in the first place. So you have something rotating, you've got the tangential acceleration, you got the centripetal acceleration. This is what's causing the rotation in the first place. And because of that, you get some net acceleration. And the relationship between those was A tan plus AC. You get the equations for kinematics. You get theta F equals theta initial plus omega t plus 1/2 alpha t squared. Omega final plus omega initial plus alpha t. Omega final squared plus omega initial, omega final squared equals omega initial plus 2 alpha theta final theta initial. And then we had the average omega, the average velocity, angular velocity. Okay. Then we had linear to angular quantities. X equals r theta v. This was tangent. I never said that before, but the linear cases are usually the tangent cases. Like, so for example, your acceleration is in this direction, so is your velocity. It's tangent to the circle. Not a big deal, really. We had a couple of things here. AC. Let's go ahead and write that. You can also rewrite omega here, actually, to get v squared over r. What the hell? We have conversions. L equals r theta. So 180 degrees equals pi radians. 1 revolution equals 360 degrees equals 2 pi radians. I should say degree to radian, or vice versa. We had this little chart that I briefly made. This was what we had. And I know this lecture's fairly long. It's almost over, I promise. 180 or pi radian, and then this is 90 degrees or pi over 2. Pi over 2 radian. Let's rewrite that. Okay. We had the rates of rotation. And I'll include this summary as like its own separate thing. I know there's a lot of equations for this. So this is our angular velocity over our total distance, because this is the circumference, right? Our total distance traveled. So we get frequency, angular velocity over total distance. The units are hertz, hz, or 1 over second, or yeah, 2 pi r, sorry, 2 pi times the radius is the total distance here. But that comes from a conversion, okay, or a derivation on that. Anyway, units are hertz, or 1 over second, or rarely rad per second. And again, this is because radians are actually dimensionless. Oops, forgot one more thing. Period, which time to complete, or time to complete revolutions. So the main difference here is when you're talking about frequency and period and stuff, it's in terms of full revolutions rather than like half revolutions or stuff like that. If you're using like half revolutions, you're going to just talk about, you know, angular velocity and angular position. So here's the period. Units are seconds. And then we had rotational forces. I know that whole bit was just kinematics. So again, we draw our circle. We have our object. We've got some thing pointing in. This is the force, centripetal force that's causing this centripetal acceleration. We'll do a couple problems with this. This was the centripetal, I'll write it like this, acceleration, the cause of rotation. Okay. We had torque. Tau equals RF sine theta. We had Newton's second law for rotation, and that was tau equals I alpha, and then linear case, right? Very similar there. I was the moment of inertia. Which changes with shapes. So changes with mass and how the mass is distributed. We introduced, with energy, we introduced this rolling energy. Okay. which is just the kinetic energy of rolling. It's 1/2 I omega squared. And remember, you still have linear kinetic energy. You had angular momentum, which is L, and L equals I omega, the linear case was P equals mv. And angular momentum is conserved. We'll do a few of these problems. Okay. Also, energy is still conserved as well. I don't know if we'll do any of those problems. Okay, so that's pretty much it for rotation. I hope this lecture was useful. Again, you can go back and refer to this, all this stuff at the end, and I hope it was useful. And I'll see you in the next one where we'll do some rotational examples.